All right, welcome. Today, we are diving deep, I mean really deep, into the heart of how data works. We're going to go way past the surface level of variables and data types and start to play with information at its most fundamental level, the individual bits. And to show you just how powerful this can be, let's kick things off with a little puzzle. So think about this for a second. How could you possibly hide a secret file, maybe a text document or even another picture, inside a normal image file without the file size giving away the secret? I know, it sounds like some kind of magic trick, right? But I promise you, by the end of this, you'll know exactly how it's done. And the key, well, it all lies in the hidden power of bits. To get there, though, we first need to change the way we think. We have to start thinking like a computer. And that means leaving our familiar decimal numbers behind and stepping into the world of binary. You see, while we humans use 10 digits, 0 through 9, computers get by with just 2, 0 and 1. That's the binary system. Every single number, every piece of information you can imagine, has a binary equivalent. It's kind of like a language with only 2 letters, and it's the language that runs our entire digital world. Okay, so here's something you really got to get straight in your head. The difference between Python's logical operators and the bitwise operators we're talking about today. Logical operators, like and or, they deal with high-level ideas of truth. Is this statement true? Is that one false? But bitwise operators, like the little ampersand and pipe symbols, they couldn't care less about truth. They operate directly on the ones and zeros that make up the numbers themselves. And to really hammer that point home, think about the idea of truthy and falsy. To a logical operator, the number 5 is truthy and 0 is falsy. Simple enough. But to a bitwise operator, 5 is just its binary code, 101, and 0 is just 0. It's not about being true or false, it's about the literal pattern of bits. That's the key difference. So with that foundation laid, we're ready to open up Python's Bitwise toolkit. These are the 6 main tools we have to perform, well, what's basically data surgery. So what have we got? We've got AND, OR, and XOR, and these guys compare 2 numbers bit by bit. Then there's NOT, which just flips every single bit in a number. And finally, we have the shift operators, which are super cool. They slide all the bits to the left or to the right. Let's see them in action, because this makes it really clear. Look at the AND operator. It looks at each vertical column of bits, one by one. If, and only if, both bits in that column are a 1, then the result for that column is a 1. Otherwise, it's 0. The OR operator is a bit more generous. It gives a 1 if either bit is a 1. And then there's XOR, or exclusive OR. It gives you a 1 only if the 2 bits are different. Now, for those shift operators. Shifting left is just fascinating. When we take the number 39 and shift its bits left by 2 places, every bit scoots over and we just fill the empty spots on the right with zeros. And the new number is 156. Now, notice something? 156 is exactly 39 times 4, or 39 times 2 to the power of 2. So left shifting is actually a lightning-fast way to multiply by powers of 2. And you can probably guess what right shift does the exact opposite. If we shift 157 to the right by 2 places, the bits move over, and whatever falls off the end just gets chopped off. The result is 39. And what's that? It's the same as doing integer division of 157 by 4. So the big takeaway here is that these shift operators are basically hyper-efficient shortcuts for multiplication and division by powers of 2. Okay, so we've got our toolkit, but how do we use these tools to change just one specific bit without completely scrambling all the others? Well, the answer is an incredibly powerful technique called bit masking. A bit mask is really just another number, but it's a number that we've carefully designed. We craft its binary pattern to act like a stencil for spray paint. It lets us isolate, change, or even just read a specific bit in another number, all while leaving the rest of it completely untouched. This is the secret to precise control. So how's it work? Well, to read a single bit, to check if it's a 1 or a 0, we create a mask that has a 1 only in the exact spot we care about. Then we use the AND operator. And since anything ANDed with a 0 becomes 0, it just wipes out all the other bits, revealing only the state of the 1 bit we targeted. Now, what if you want to set a bit, to force it to be a 1? Easy. You use that same mask, but this time with the OR operator. This forces that one target bit to become a 1, while all the zeros in the rest of the mask make sure that every other bit in your original number stays exactly as it was. Pretty neat, huh? Unsetting a bit, or clearing it to 0, is a little more clever. First, you take your mask and you invert it with the not operator. So now it has a 0 only at your target position and 1s everywhere else. Then you use the AND operator. That forces your target bit to become a 0 while everything else stays the same. And finally, my favorite one, toggling a bit. To just flip it from 0 to 1 or 1 to 0, we use the XOR operator. This is just brilliant. If the target bit is different from the masks bit, a 1, it becomes a 1. If it's the same, it becomes a 0. It's literally a perfect switch. So there you have it. We now have all the tools we need. Let's circle all the way back to that first puzzle and finally solve it. How do you hide a file in an image? First, let's just be super clear about what we're doing. This isn't cryptography, which is all about scrambling a message so it's unreadable. No, this is steganography, which is all about hiding the fact that a message even exists in the first place. Our goal is to make the communication itself totally secret. So here's the game plan. We take 1 byte, that's 8 bits, from our secret file. Then we go and grab 8 bytes of data from the image's pixels. Now, for each one of those 8 image bytes, we're only going to change its very last bit. This is called the least significant bit because changing it makes the tiniest possible change to the overall color value. First, we use a bit mask to clear that last bit, setting it to 0. Then, we take 1 bit from our secret byte and write it into that now empty spot. We just do this 8 times, hiding 1 secret bit in each of the 8 image bytes. And what's the result? Have a look. One of these images is the original. The other one, it has a whole other file hidden inside it using this exact technique. Because we only change that very last bit of each color value, the change is so small, it is completely, utterly invisible to the human eye. How cool is that? Now, this isn't just a cool party trick. This kind of low-level control is actually fundamental to all sorts of programming, and it pops up in a lot of surprising places. Bitwise operations are used for super high-performance calculations in data science libraries like NumPy. They're used to build incredibly efficient database queries. And they're used for a classic technique called flags, where you can pack a whole bunch of true-false settings, like a user's permissions, all into a single compact integer. So we've seen that Bitwise operators give you the ultimate control over your data. They let you perform crazy fast calculations, pack information in super efficiently, and yes, even hide secrets in plain sight. It's a powerful reminder that underneath all the complex layers of modern software, it all just comes down to ones and zeros. So the only question left is, now that you can control the bits, what will you create?